So consider a situation like this. So you have a light ray with intensity I that is traversing a slab of material here, this cube. The intensity in general is going to be both removed from the beam by absorption events and then added to the beam by emission events. So the intensity that is going to come out from interaction with matter in this cube is going to be modified by amount di. That's the question that is set here. You have a ray of intensity I traversing a medium, say of side ds, and the intensity that is going to come out is going to be modified by an amount di. What is the intensity that is emerging from this cube? What is the amount of intensity di that is either added or subtracted from the beam? So let's consider these absorption and emission events separately. Let's consider first absorption. In the absorption case, the quantity di is going to be negative. Intuitively, we can say that the amount of radiation that is removed will depend on the size of the slab, because a bigger slab means that there is more material absorbing. We can also expect that it's going to depend on the density, because a higher density means that there are more absorbers packed per volume. Another thing that we can think of is that it's going to depend on the intensity of the radiation. After all, if there are no incoming photons, there is nothing to be absorbed. So based on these notions, we can write a proportionality that the intensity coming out is going to be negative, is going to be proportional to the density of the material, is going to be proportional to the size of the slab that had to travel, and proportional to the initial intensity that is shining through. Here, I'm dropping the subscript nu for clarity. So this is a proportionality. The differential of the intensity is proportional to the intensity, the density, and the size of the slab. We can replace the proportionality by an identity by defining the opacity as a proportionality factor. If you call the opacity kappa nu, then you can write this equality. Then you can write this proportionality as an equality. The opacity quantifies the resistance of matter to the passage of radiation. It is a quantity that depends on the frequency, because a material can be at the same time transparent in one wavelength while opaque in another. Glass, for instance, is transparent in visible wavelengths and opaque in infrared. So this cube has a density and an opacity associated with it. Now, because these two quantities, the density and the opacity, often come together, it's frequent that we define a coefficient alpha, that is the opacity times the density, and call it the absorption coefficient. Notice that you have intensity here on both sides, so we can easily integrate to this equation. You have a log here on the left-hand side, so this becomes an exponential of the integral of the right-hand side. Because you have this integral and an exponential, we can simplify the notation by defining this as another quantity that we're going to call the optical depth. We can define the optical depth infinitesimal as the right-hand side of this equation. And thus the optical depth is the path integral of the absorption coefficient. Again, keep in mind that the optical depth indeed depends on the frequency. So in fact, this would have little subscripts here for the frequency. I'm just dropping them for clarity in the notation. So with that, you can substitute this integral in the result we got for the intensity to find the absorption law. So what we find is the radiation is attenuated as it travels through the medium. The attenuation increases rapidly with optical depth, and very rapidly, because this is an exponential. Indeed, you can see that for tau equal to 5, only about 0.007 of the original radiation escapes. For tau equal 10, you have an exponential minus 10. That means that in this case, only 5 times 10 to the minus 5 of the original intensity escapes.